In this final section, we want to go ahead and sketch rational functions. And to do that, we need to study the behavior around vertical asymptotes. Like polynomial functions at x-intercepts, whose behavior is determined by the multiplicity, we'll see that the behavior of rational functions around vertical asymptotes is determined by, number one, a factor in our rational function, and number two, the degree of that factor. Before we look at that, let's go ahead and look at a simpler example. Here we're given the graph of y is equal to 1 divided by x raised to the k, where k is even. The graph of the following function looks as such, and it has a vertical asymptote at x is equal to 0. And the thing to note is that when the degree of our x raised to the k is even, then both sides of our graph are going to be approaching infinity as we approach our x value of 0. And by a mirror argument, we'll have that y is equal to negative 1 divided by x raised to the k, where k is even. Both our y values are going to be approaching negative infinity as our x values are approaching 0. And now if we look at the function y divided by x raised to the k, where this time our k is odd, then as our x values approach 0 from the right, our y values are going to be approaching positive infinity. And as our x values approach 0 from the left, our y values are going to be approaching negative infinity. And if we have y is equal to a negative 1 divided by x raised to the k, where k is odd, we're going to have the same behavior that's been flipped over the x-axis. Now we can extend these ideas to rational functions where vertical asymptotes are given by factors in the denominator. Let's do this by looking at an example. Suppose we're given the following rational function with the following graph. Then the denominator is telling us about a vertical asymptote. We'll have one at x is equal to a negative 3 and another one at x is equal to 2. If we have a vertical asymptote whose corresponding factor has even multiplicity, then the graph is going to look like y is equal to 1 divided by x raised to the k, where k is an even number near our vertical asymptote. And in this picture here, we have x plus 3 corresponding to the vertical asymptote x minus 3, and we see that near our vertical asymptote, our graph looks like the graph of x 1 divided by x raised to the k, where k is even. And the other case, if we have a factor corresponding to a vertical asymptote with odd power, so for example, this one here, then y looks like the graph y is equal to 1 divided by x to the k, where k is odd. And this can be seen in the graph by this piece here. Now to determine if the y values are going to positive infinity or negative infinity, we'll have to use a few different test values to check. Let's also go ahead and review what happens to our x-intercepts. So our x-intercepts are given by the zeros of our numerator, which can be found up here. And again, if an x-intercept has odd multiplicity, then our graph crosses at that x-intercept, and if our graph has even multiplicity, then it touches. So for example, x plus 1 corresponds to the x-intercept at x minus 1. So this is going to be our x-intercept at x minus 1. And since this has an even multiplicity, it is only going to touch. And this term over here corresponds to our x-intercept at x is equal to 3. And since it has an odd multiplicity, it crosses. Let's go ahead and look at a problem where we sketch the graph of our rational function. So here we're given our function, and first, let's go ahead and check for the vertical asymptotes and the removable discontinuities. So we see on the top and the bottom, there's no common factors, which means we're not going to have any removable discontinuities. But we will have vertical asymptotes at x is equal to 1 and also at x is equal to 3. And we can go ahead and note that the power of the term corresponding to the vertical asymptote of x is equal to 1 is 2. And the power of the term corresponding to the vertical asymptote of x is equal to 3 is 1. Now, we can go ahead and look at our horizontal asymptote and our slant asymptote, since we have that the degree of p of x is equal to the degree of q of x. This implies that we'll have a horizontal asymptote at y is equal to the leading term, so AP divided by the leading term BQ. And this means we'll have no slant asymptote. So to find the leading term, we can just go ahead and multiply the first term of our top polynomial. So this is going to be given by x plus 2 times x plus 2 times x minus 2. So multiplying this first term here, we'll get an x squared plus some other stuff that we don't care about times an x minus 2. Again, multiplying these first terms here, we'll get an x cubed plus a lot of stuff that we don't need to compute. This means the leading coefficient of our numerator is going to be equal to 1. And we can go ahead and do the same thing for this bottom piece here. So multiply out our x minus 1, x minus 1, x minus 3. All this is multiplied by 2. Again, we can see by a very similar train of thought that this is going to be equal to 2 times x cubed plus some other numbers here. And this means we'll have a leading coefficient given by this 2 here. So this is going to be 1 divided by 2. Now let's go ahead and find the x and y intercepts of our function. So to find the x-intercept, we'll set y is equal to 0. So 0 will be equal to an x plus 2 raised to the second times an x minus 2. And since if we multiply the denominator on both sides, it'll cancel the bottom out, and we'll still be left with a 0 on the left-hand side. So we can really just look at the numerator. Now solving for the zeros of this equation, since this equation is given in factored form, we'll know we'll have a 0 at x is equal to a negative 2, and we'll have a 0 at x is equal to 2. And the multiplicity of each of these x-intercepts is given by 2 and 1. And so lastly, we need to go ahead and find our y-intercept. So y is going to be equal to where we plug in x is equal to 0, so this will be 2 squared times negative 2 divided by 2 times the negative 1 squared times the negative 3. Simplifying this, we'll get a negative 4 on top, and on the bottom we'll get just a negative 3. And so we'll have a y-intercept at 0, 4 divided by 3, and we'll have an x-intercept at negative 2, 0, and 2, 0. We can go ahead and sketch this graph now. So we'll go ahead and write out the horizontal and vertical asymptotes first. So we have vertical asymptotes at x is equal to 1 and x is equal to 3. Then we have a horizontal asymptote at y is equal to 1/2. And we have x-intercepts at negative 2, 0, 2, 0, and we have one y-intercept at 0, 4 divided by 3. Now we can fill in the rest of our information. Number 1, we know that the x-intercept at 2, 0 has a multiplicity of 1, which means it's going to cross here. And we don't know enough information, so we're going to have to put in a few test points to look at the behavior of our rational function. So let's go ahead and start a new page. And we'll plug in some points to see what's going on. Well, another thing we do know is the multiplicity of this is even, which means our graph is only going to touch here. And since we know it has to hit our y-intercept, our graph should look something like this. Now, since the factor corresponding to our asymptote x is equal to 1 has an even power, then the shape of our graph will look something like this. And again, since the multiplicity of this 0 here is odd, our graph is going to pass through. Now, since this vertical asymptote corresponds to a factor with odd power, then our graph should look something like this. And so this is a sketch of our graph. Let's go ahead and just draw another picture just to clean it up a little bit. So our final picture, our graph will look something along these lines. And we're done.